Welcome to Pomodoro Joe for Thursday, February 16th, 2023. Today we're doing LeetCode problem 104, maximum depth of binary tree. We got an easy one today, folks. So, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. And here we have a representation of a binary tree. Now, anytime you hear something about binary trees, you should immediately think recursion. Recursion is often a good way to handle binary trees. So with that, we'll put 25 minutes on the Pomodoro timer and get started. I bet we can get this one down to one line of code. What do you think? All right, let's give it a shot. So being an easy problem, I am going to go through this a little bit slower. I'm going to explain all the steps in the process, and then we will eventually come down to have one line of code. So how do we solve this one? Well, let's start by making our maximum depth a recursive function. So what is a recursive function? A recursive function is just a function that calls itself. How does that work? It's kind of like magic, but it works. So with a recursive function, there are two things that you need. You need a base case, and the base case is the end case where you don't have any more work to do and you can just return from the function. Then you need the recursive case. The recursive case is where you've broken down the problem by a little bit and then you call the function itself from within the function. So we will actually be calling max depth from within max depth. The way this will work is we will start at some root node, and then we will call max depth on either the left node or the right node, or perhaps both nodes. As with most of my functions that have a return value, I will start with some result, and we'll set it to 0. And at the very end, we will return our result. Now we want to define our base case. So what is the base case on this function? What is the case where we don't have any work to do? Well, that's when this root, as you can see, it's an optional. If this root is none, there's no work we can do. There's a 0 depth on this tree, and we'll just return 0. So if root is none, we return 0. Or we can say return result, because we've set it to 0. So now what's the recursive case? So the recursive case, now in this case we've got our root node. We know that we have one because we've passed our initial conditional here. Now this root node can have a left node and a right node. And how do we calculate the maximum depth from our root node? Well, we look at our root node and we have at least one node, so in that case our result will be equal to 1. And then we have a left branch and a right branch. So we look at the left branch and we see how deep that left branch goes. What's the maximum depth on the left branch? And then we look at the right branch and we see how deep the right branch goes. And what's the maximum depth on the right branch? Now the maximum depth for this tree will be 1, our root node, plus the maximum depth of either the left or the right, depending on which one is deeper. So we'll just calculate both. We'll look at left, so we have two options. We have option 1, the left option. I'll call this option left. And we have option right. Now, what are the values of the option left and option right? Well, that's the depth of the left tree and the depth of the right tree. How do we calculate the maximum depth? Well, we have a function for that. In fact, it's this function itself, max depth. So we'll just call self.maxDepth. The self is because this is a class-based solution, so self has to be put in front of max depth. It's not anything to do with recursion, so don't let that confuse you. We will call self max depth on, well, in this case, this is our left branch, so we can call root.left. And just as we were trying to find the maximum depth of our left branch by calling max depth root left, we will do the same for the right branch. To find the maximum depth of the right branch, we call self max depth on the root's right branch. Now finally, how do we get our result? Well, we'll say our result will be our one root node plus whichever branch has the deeper depth. So that's going to be the maximum of our option left or our option right. All right, I think that should do it. Now let's see how many typos I made. Didn't make any typos this time. All right, pat myself on the back a little bit for that. So here we have a basic recursive solution. The recursive solution has the base case, which is just we have no more node, we just return our result. And we have a recursive case where we say we have our root node plus the maximum depth of either the left or the right, whichever one's deeper. All right, let's submit this and see how well we do. Not too bad for a first attempt. We beat 88% for runtime and 49% for memory. Okay, now I know I promised at the beginning of this video that we would break this down into a single line solution. So here's how we refactor this solution into a single line. Now the first thing we have to do is let's move this, since this is just saying if we don't have a root, we can return the result. Well, we don't actually need a result yet at this point. So we can get rid of this. We don't need that. We still have our base case, but we'll return 0 because that's what happens when you have no tree at all. All right, so we'll say if the root is none, we'll return 0. And now this result is 1. And we have option left, option right, and we have this result. So this result here is just 1. And it won't be plus equals anymore, it's just plus. So let me explain this a little bit. So this result is 1 to start with. And we're just adding this to that 1 and we're returning it. So this is the same thing as just saying 1 plus this. So those are equivalent. This is 1. We were returning that. So we can actually just replace that whole thing with a return. We don't need this result anymore. All right, so we still have our base case and our recursive case and our return. So we can get rid of these intermediate variables left and right by just replacing both of them with what we've assigned them to here. So we can just replace these with the recursive call itself. Okay, we're getting super close to one line. We still have 3 lines of code here. All right, let's clear out some of our comments. And how do we reconcile the rest here? Well, we can say we'll return this if the root node is not none. Or let me do this, sorry, I'll do this a little bit better. Okay, so how do we reconcile this last piece? If the root node is none, we return 0. Otherwise, we will return our maximum depth. Well, we can rearrange this a little bit by saying, let's return 0 if the root node is none. Else, so that's if it's not, then we can get rid of all of this. And there we have it. There's our one line of code. We will return 0 if the root is none. Otherwise, we'll return 1 plus the maximum of either the depth of the root's left branch or the depth of the root's right branch. Let's make sure this still works. All right, one line of code. Let's see how you do. Hey, it passes. It does not do as well with our runtime. We only beat 46? No, we beat 48% for our runtime and beat 18% for our memory. So this just goes to show that having compact code doesn't necessarily always result in the best runtime. All right, so this one is fun. I really like recursive problems like this. Check this one out. Again, this is LeetCode problem 104. Check it out, try it on your own, See if you can do better. I only got an 88% runtime. See if you can get a 90% or better. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code than me.